Relays. Relays in HVAC are really common. They're in pretty much all of our electronic devices that are in your HVAC equipment now. They're in fan centers, they're in modular motors, but they're everywhere. So in order to be proficient at and understand how they work, we first must need to know what they're made of and how they operate. So HVAC and relays are nothing more than an electrical device consisting of a coil and a set of contacts. Our coil is right here. Our contacts are right here. Okay, the coil and the contacts are isolated from each other. They are protected. Under those two parts of the coil do not touch in any way. Okay? However, they are designed to be usable where one circuit must control another. So how do we able to do that? Well, we need to have a relay coil. Okay, the relay coil is a spool of wire that is wrapped around an iron core. And when we energize that wire with electricity, we generate a magnetic field. So here is my coil of wire right there. Okay, my power that would be energizing this coil is connected right here. And right here is that iron core that we were mentioning. Okay, right there in the center. So when I energize this coil, I generate a magnetic field, this coil of wire. Okay? And then that magnetic field pulls an armature, which will then close or open a set of contacts. When a relay is shown in a schematic, it is always going to be shown in its de-energized mode. So when we're looking at schematics and we see relays, we got to kind of use a little bit of imagination. We got to visualize a switch closing or whatever is controlling it, controlling our coil, and imagining what happens once that coil gets energized. What contact's going to open, what contact's going to close. Every coil has a voltage rating on it. Okay, and these ratings is the voltage that you may use and have to use to apply to the coil. So these ratings can be anywhere between 24 volts, 120, 208, 230, you name it. However, you may not apply, say, 120 volts to a 24 volt coil. You may not apply 24 volts to a 120 volt coil. You can't do it. You have to put the correct voltage to the coil in order for the relay to work properly. If you were to apply 120 volts to a coil that was rated for 24 volts, you will melt the coil. You will probably set the coil on fire. You're going to damage the coil. You're going to damage the relay no matter what. If you were to apply 24 volts to a coil that was rated for 120 volts, you would not generate enough magnetic field to change the armature to open and close the contacts. The coil rating is normally stamped on the side of the relay. It's going to be on the nameplate. And the coil is going to be the load in a schematic diagram. Okay, the coil is what does all the work when it comes to a relay. The contacts on a relay are attached to an armature that is moved by the magnetic force of the coil. So relay contacts have metal points that come in contact with each other, and it's these 2 points that makes the circuit. Normally open contacts are the equivalent of an open switch. Okay, when the relay coil is de-energized, those contacts are going to open the circuit. When the relay coil is energized, they can close those contacts just like a light switch. And then when that coil is de-energized again, they're going to open. When the term normally closed is used, it is going to be the term where the contacts are going to be in their normal position when the coil is de-energized. When the coil is energized, that contact is now going to open, which is then turning off the voltage. Therefore, it's going to shut off a load. And when that coil is de-energized again, those contacts will close. Remember, once our normally open and normally closed contacts are energized, they are going to do the complete opposite. Our normally closed are going to open. Our normally open are going to close. The contacts are rated with the number of amps they can control. The contacts are also rated with the type of load they can control. Okay, this would be an inductive load like a motor, or it could be a resistive load like a heater. We will run into a lot of resistive heaters if we're dealing in refrigeration for, say, like electric heat, electric defrost. You're going to run into it in heat pumps if we're using supplemental or emergency heaters in the ductwork. That's where you will run into stuff like that. But either way, a relay is going to be used to turn that stuff on and off. An inductive load, the amperage spikes when that motor initially starts. And if we're dealing with a resistive heater, the amperage is going to remain constant. But regardless of what it is, whether it's an inductive load or a resistive load, we need to make sure that the contacts are able to handle the amperage that's going to go through it. If we don't do that, the contacts are going to overheat, and they can actually weld closed, or they can weld open. Either way, we're going to damage the relay. So we need to make sure that the amperage is rated properly for whatever we're using that relay for. When the relay is de-energized, there is no power across the coil. The contacts between 1 and 3 are normally open. The contacts between 1 and 2 are normally closed. So when the relay coil is energized with, say, 24 volts, this is going to close the contacts between 1 and 3 and open the contacts between 1 and 2. When you see the coil and relays on a schematic, these are the symbols that you're most likely going to run into. You have your coil, which is doing all the work. You have our normally open and our normally closed contacts. Okay? Between our normally open, we have terminals 1 and terminals 3. Between our normally closed, we have terminal 1 and terminal 2. So anytime I energize this coil, this set of contacts is going to close. This set of contacts is going to open. Remember, they're going to do the complete opposite than what they are normally in. Again, a relay is designed to control loads in the same circuit or another circuit. So let's take a look at this example. Right here we have a relay that is controlling 2 loads. We have a normally open contact, normally closed contact, and here's our coil. But notice in this diagram, our switch is in the open position. When that switch is in the open position, the coil is not energized. So therefore, I am not generating the magnetic field necessary to change those contacts. So in other words, the relay really is just at rest. It's not doing anything. Okay, so I have my power coming through my L1, down through my normally closed, through my load, and then back to neutral. This load is what's operating right now. This load is not. This load is not working right now. Why? Because my normally open is open right now. I'm not doing anything. However, once I close my switch and I energize my coil, I am now generating that magnetic field. Notice what happened to the contacts. My normally closed has now opened, and my normally open has now closed. So now I have power going through my normally closed, and now this load is now operating. because I am now generating the magnetic field necessary to make these two contacts change. Okay, the Mars relay is probably one of the most frequently used relays out there, and that's what you're most likely going to see a lot of. It consists of a coil and two sets of isolated contacts. Again, you're normally open and you're normally closed. Each set has a normally open and a normally closed contact. And if we were to look at a relay or a Mars relay, this is what we would kind of see. All of our designations are numbered. And if we were to look at it, we would actually have this very diagram on it. It gives us our designations. Here is terminal 1 and terminal 3. It's normally open. Our terminal 1 and terminal 2 is normally closed. The same thing applies for 4 and 6 and 4 and 5. Terminals 1 and 4 is our L1s, our power coming in to our relay. Terminals 3, 2, 6, and 5 are all going out to our loads. Okay? And here is our coil, our power coming in. So I'm going to say here this is getting powered with 24 volts. Okay? So once I apply power to my coil of 24 volts, I am now energizing this coil, which is generating the magnetic field, which will make these contacts now switch position. When it comes to troubleshooting a Mars relay such as this, it's relatively simple. All we have is a coil and a set of contacts. We can troubleshoot this with resistance. Okay? The coil is the load. So we're going to be using electricity to generate electrical magnetic field. So therefore, if that's a coil, I am going to, most likely, if it is good, I am going to read some resistive numbers, some ohm reading. 25 ohms, 50 ohms, 10 ohms, 5 ohms, whatever it's going to be. If I'm reading OL across that coil, it's telling me that my coil is broken, it's open. It's no good. If I read 0 on it, it's telling me that I'm shorted. My coil is shorted somewhere. It's no good. And if I don't get anything like that, I am not going to change the magnetic, I'm not going to generate the magnetic field, and therefore my contacts are not going to change. Now let's look at it from the switching side of it, the switches. Terminals 1 and 3, that's normally open. Remember, when it's in its de-energized state, this is open. So I should read on my meter, OL. If I'm reading 0 across this and this coil is de-energized, it's telling me that this switch is actually welded closed. It's no good. Remember, normally open is when it's in a de-energized state. So I should be reading OL there. If I'm going across 1 and 2, I should be reading 0. Why? Because that's a normally closed switch. A switch is a power passing device. It has no resistance. I should be reading 0. If I read OL here, that's telling me that my switch, my normally closed switch, is open. And the relay needs to be replaced. There's nothing we can do to repair it out in the field. We take the relay out, we put a new one in, and wire it. And that is your sequence of operation and how a relay works.